All right, so welcome back. I'd like to start by pointing out that despite what you might think, I'm not the most skilled lecturer around, and I hope these talks are useful. But I want to remind you that they're best used as complementary to the various other resources that are out there. In particular, today's lecture is best appreciated together with the discussion of interval estimation in the book by Miller and Miller, for example, in which it's covered in sections 11.1 and 2, at least in the 8th edition. And I'd also recommend Knudson's lecture on confidence intervals for means using the central limit theorem. So I'll put that in the notes. All right, so let's go ahead and begin. What's the plot? Well, we have some population, and that population has certain features. So the population we think of as being modeled by some distribution, some probability distribution. That population has some features that we're interested in knowing about, with some features which are going to be described by various parameters. And these might include such things as so the population we're thinking of as just a set of numbers that we're drawing, the kind of results of our experiments or something like that. And it has some parameters. So for example, it might have, it'll have some mean, it'll have some variance, sigma squared, but there might be various other parameters, like maybe the population's distribution is described by some exponential random variable, or in which case it'll have some lambda or some other parameter that naturally describes that distribution. Okay, well, in any case, there are some parameters, and we want to know them. So what do? We take some measurements, some x1 through xn, which we think of as identical, independently distributed random variables, but with the distribution that describes the population. And what we'd like to do is we would like to estimate parameters of interest using these measurements. So the natural example and a good place to start is, you can calculate, for example, the sample mean, which we described before, the sample mean, x bar, which is just the average value of these random variables, and we can ask how well does x bar approximate mu? So we've talked about this before, but let me put it in a slightly different language, right? So the goal of such an endeavor is to come up with some sort of statement like, so we want a statement of the form, we are 95% certain that mu is between x bar minus, 3 and x bar plus 3. So that would be a great kind of statement to be able to make. In terms of probability, we might say something like the probability that the random variable x bar minus 3 is less than or equal to mu is less than or equal to the random variable x bar plus 3 is 95%, 0.95. Okay. So in other words, the interpretation of that is that, if we actually measure and get some value, little x bar, some measured value for the sample mean, then we are, so if we're given some measured value, we're 95% certain that that x bar minus 3 is less than or equal to mu is less than or equal to x bar plus 3. That's the kind of human interpretation of that statement. So I want to formalize this this particular language with the notion of a confidence interval. So this is this definition, the definition of a confidence interval. So here's how it goes. If we have, let's say we have some random variables, or I should say, if we have some parameter first, say call it theta, lowercase theta, which has to do with our population. And if we have random variables, capital theta 1 bar and capital theta 2 bar, such that the probability that this random variable less than or equal to the population value less than or equal to, well, let me just say strictly less than to conform with conventional notation, is equal to 1 minus alpha. So if we have this for some value alpha, and if little theta 1 and little theta 2 bar are measured values of capital theta 1 bar and capital theta 2 bar, then we say little theta 1 bar less than or equal to theta less than or equal to little theta 2 bar is a 1 minus alpha confidence interval for theta. We say that theta 1 hat, little theta 1 hat and little theta 2 hat are the lower and upper confidence limits. And 1 minus alpha is called the degree of confidence. Okay, so this is the problem that we're interested in. We are interested in finding these confidence intervals for particular parameters of interest. We're interested in finding these random variables, capital theta 1 and theta 2. In the case up above here, it was x bar minus 3 and x bar plus 3, which give good bounds with some particular degree of confidence on the parameters of interest. It's important to note that these are not unique. There might be plenty of different confidence intervals that are 95% confidence intervals for the same parameter, like kind of shifting things a little over to the right or left, for example. And we'll have some discussion about what are some desirable properties of these intervals might be. So the natural question then is, how do we find these confidence intervals? So we're going to take a look at a case that we've really already looked at. I'm just going to say it a little bit differently. And that is, how do we get a confidence interval for the mean, the kind of first example we looked at. On the other hand, in the future, we're going to be very interested in other parameters. For example, the variance is going to be a really interesting one to look at. We'll look at that next. But so let's talk about the mean first. So as we've already said, the estimator that we're going to use, the thing that we're going to use as a kind of proxy for the mean, is the sample mean. And the thing that's going to make that particularly nice to think about is via the central limit theorem. If we're taking a lot of samples, if kind of n is big, then the sample mean is going to be approximately a normal random variable. So being a normal random variable, the only information that we really need to know about the sample mean, so remember the sample mean is just the sum of these n independent identically distributed samples, these random variables xi, and divided by n. And so if this is a normal random variable, then all we really need to know about it are its mean and its variance, and that's going to describe it as a random variable. So as we noticed before, the mean of the sample mean is the mean of the population, and the variance of the sample mean is the variance of the population divided by n. And so then we can talk about x bar in terms of a normal random variable. And that looks something like this. So if we want to take our standard normal random variable and relate it to our x bar, well, by the central limit theorem, this is going to be, I guess I should say approximately, our random variable minus its mean divided by the square root of its variance, this kind of standard deviation. And so for our particular case, what we've just said is that the mean of the sample mean is the mean of the population, and the variance of the sample mean is going to be the variance of the population divided by n. And that tells us that this quantity right here is a normally distributed random variable, is the standard normally distributed random variable. All right, so getting back to our problem then, so if we have the knowledge that this particular combination is our standard normal random variable, the problem that we're going to be faced with is, as always, want to estimate the mean of the population in terms of the sample mean. And of course, there is this extra bit of information here, which is the sample variance, or its square root. And so we're going to just assume, for simplicity, that we know the variance of the population. And this is just an assumption that we're going to make for educational purposes. Okay, so suppose you know the variance of the population, and you want to estimate the mean of the population using the sample mean. Well, what this tells us is that if we look at this particular combination, then this is a normal random variable, and so it's easy to make some estimates and say something like, well, you know, I have a reasonable way of saying what's the probability that my normal random variable is, I don't know, between -2 and 2, right? So I can, you can look up on a chart and find, a nice expression for this. There's a very high probability that this is true. And then what does that tell us? So if you know, let's say that this is equal to some particular 1 minus alpha for some reasonably small alpha, well, rewriting this on the inside, I find that, so remember, sigma is known here, and of course n is known. So with this particular probability, I know that I have this series of inequalities, that this is less than that, and also that x minus mu is less than 2 sigma over root n, which I can then, Then if I rearrange this by moving the mu over and moving this thing over there, I get that mu is less than x bar plus 2 sigma over root n, and mu is less than, mu is greater than, I'll move it on to that side, mu is greater than x bar minus 2 sigmas over root n. And so I can rewrite this, so this is really the same set of inequalities. So if I use that to rewrite this, then what I find is that with that same amount of certainty, that mu is between x bar minus 2 sigma over root n and x bar plus 2 sigma over root n. Translating that into the language we had before, what we're really saying is that if we call x bar minus 2 sigmas over root n our random variable theta1, and if I call theta2 at x bar plus 2 sigma over n, then what I get is a confidence interval for mu of the form any particular measured value of this less than or equal to mu, less than or equal to some measured value of this, which really just depends on my measurement of the sample mean, is a 1 minus alpha confidence interval for the mean. Okay. So these are two particular statistics, two particular random variables, depending on my sample, which give me a confidence interval for the mean.